main question is, can a user tell if they are using a quantum network? Remember, I said that users are classical. They're only going to see the classical data going into the network and the classical data coming out. We can label this classical input as X and the classical output as Y. So you'll put an input into the network, you'll get an output. You put another input in, you get a different output. Over time, you collect lots of data, and that data produces or can be used to estimate a probability distribution. Now, this probability distribution can actually describe what that network does. Now, the challenge is your classical device will connect into some black box hardware. Let's just assume it's a black box. And the question is that black box hardware actually quantum and connecting to a quantum network? Or is it connecting to an adversarial classical simulation? So here, this adversarial classical simulation, it would try to trick a user into thinking that it's connected to a quantum network, but really it's just classical underneath the hood. It's just a simulation that's done using a classical computer. So if this were the case, any secure protocols that the user thinks that they're doing aren't actually secure, and all that data could be copied by the adversary. So this is the ideal attack because users continue to use their secure quantum channels and the adversary has full access to the data. So there's really renders quantum security totally insecure. And to do this, a simulation software such as Aliro's Quantum Network Simulator would only need to reproduce the probability distribution that describes the network, something that can easily be done with classical software in many cases. So to create a secure quantum communication system, we need to be able to distinguish when we're connected to a quantum system using quantum resources from a system that is simulating those quantum resources classically. And the interesting thing is that this problem actually mirrors the historic development of quantum mechanics. The way that we were able to tell that entanglement exists in nature can actually be applied to quantum networks to know if entanglement is being used in entanglement network-based infrastructures. So our main focus is how do we certify quantum resources in quantum networks? So here, provable quantum security requires that your network has ideal quantum resources. So we want to be able to tell that we have a quantum network under the hood rather than some classical simulation thereof, which is insecure. Furthermore, the quality of quantum resources needs to be tested and monitored over time because, as I previously noted, entanglement doesn't stick around very long. It's constantly produced and constantly being used. So we need to constantly monitor how good that entanglement is. We need a certificate of quality for entanglement. Now, to achieve the certificate, there's kind of two approaches, and they're both very similar. It's just a very subtle difference. In the first, you have quantum resource certification. When you are certifying a quantum resource, you have a trusted third party or referee whose goal is to test the presence and quality of a network's quantum resources. On the other hand, quantum resource verification has a network user who wishes to verify the presence or quality of a network's quantum resources. So the key difference is the certification has some trusted third party who creates a certificate for the network, where verification is a user wants to verify that certificate or the quality of these resources. Now, just to reiterate, certification and verification consume quantum resources. Furthermore, quantum resources are constantly being produced. So in order to get a good certificate on your resources, you must constantly monitor your resources in a way that the entanglement source is unaware of. The entanglement source can't know when it's being tested for quality versus when it's being used for secure protocols. In this way, we can create a certificate that accurately